Yeah, good evening everyone. So this is algebra session and I have got one algebra session where we look at properties of natural numbers and what are operations like addition, multiplication and so on, and another set of integers. And we have seen some more properties in number theory about particularly these two sets. Yeah, so we want to go one step further. What's next after naturals and integers? So we have set of rationals. And it is denoted by Q. So set of rational numbers. Q stands for quotients. And what is exactly set of rationals? So they are numbers of the form integer by non-zero integer. So A by B, where A, B are integers and B is non-zero. We don't divide by 0, right? So that is set of rationals. So for example, 1 by 2, 2 by 3. So numbers which we call as fractions, they are all rationals, right? What about integers? So shall I say is set of integers subset of Q? So is every integer a rational? So for example, suppose I have say 1. 1 I can write as say 1 by 1 or 2 by 2 or 3 by 3. In fact, a rational you can express in infinitely many ways, right? So 1 I can write as 2 by 2. So it's in this form, integer by non-zero integer. And in that sense, it surely belongs to rationals, right? So I can surely say that set of integers is subset of rationals, right? So a hierarchy N is contained in Z, Z is contained in Q. Super good. Yeah. Now on set of rationals also we have operation of addition and multiplication, which we denote by dot. And how do we define addition? A by B plus C by D is equal to, how do we add? So we cross multiply AD plus BC upon BD, right? Or another way to look at same thing is you make denominators same. So A by B I can write as AD by BD. C by D I can write as BC by BD. So I make denominators same, and once denominators are same, you can simply add the numerator part. So it's AD plus BC upon BD, right? How do we multiply? So A by B into C by D. We multiply as AC upon BD. So we simply multiply numerator, that is the upper part, divided by, we simply multiply denominator. Is that okay? Now question is, on same lines, if I say, or if I define A by B plus C by D as, simply add numerator upon denominator. What's wrong in this? I mean, why we don't do it this way? Yes, we want.
So because if the denominators are different, you can't add them.
Why?
I don't know.
So that's the question. Like, why we can't define it this way? A plus C upon B plus C. Yes, Bhairav.
Chicken is also raising hand. Okay. So Hello?
You got children?
Sir, actually, I want to say the answer to why a plus b by b plus b function. Hello, sir.
Hello, Achudan.
Yeah, sir. Actually, it's not necessary that b always divides d or d always divides b, so they can result in a totally different number, and that may not be the LCM of the fractions. That may not work.
But why we should take LCM?
So we do not know if the fractions are equivalent. That is, so if let's say take a circle with divided into certain parts, and both parts may not be same, so we have to divide it into divisions such that each part is same, so that will be easy for us to verify.
Okay.
So we should have so the denominator should be equivalent. So we have to find the LCM of both b and d.
Yes. Yes. So we have concept of what is called as equivalent rationals or equivalent fractions. So, for example, 1 by 2 is same as 2 by 4. That is same as 3 by 6. That is same as 4 by 8, and so on. All of you agree? So they are all same, right? Now, suppose if I define my addition this way, a by b plus c by d is equal to a plus c upon b plus d. Okay. So, for example, let me take say half plus 2 by 3. And according to my definition, it will be 1 plus 2, 3 upon 2 plus 3, 5, right? So that would be one answer. But somebody may say instead of half, I'll take 2 by 4. That's more convenient for me. And then for him, answer will be 2 by 4 plus 2 by 3, which would be 4 by 7, according to my definition. And though these numbers are same, the final answers are not same, right? 3 by 5 is not same as 4 by 7. So my definition of this definition of addition is not compatible with the various forms of rationals, right? So if I take different forms of rationals, it won't give me one and the same answer. So it's not well defined. Is that clear? Bhairav has raised the hand.
Also one more issue, because here you can define it to be in lowest terms and then just take 3 by 5. But the issue would be because the rationals are an extension of the integers.
Yes.
If you take this sort of addition and add 0 and 1, you get 1/2.
Right. Yeah. So that's one more nice example. So if I take say 1 plus 1, that would be no. What do you want to say? This is 2 by 2.
I said if you take 0 plus 1, you get 1/2. And if you take 1 by 2, you get 3 by 2.
0 plus 1 is half. Is that so?
It is not. But if you take this method, you will get 0 plus 1 by 1 plus 1, which is 1 over 2.
Oh, yeah,
Which
yeah.
is wrong.
Yeah, 0 by 1 plus 1 by 1. That is 1 by 2. Yeah. So this is surely wrong. Yeah. Good. This is a nice example. How about you? Yeah. Is that okay? Is that clear, everyone?
Yes, sir.
Yeah. Shall we go ahead?
Yes.
Okay. So we have set of rationals, and even the operation of addition, multiplication, they can be extended to this larger set, and in such a fashion that if I take two integers, whatever answer I used to get earlier in integers, same answers I get even in rationals, right? Okay. Now, there are some numbers which you can't express in this form, integer by integer. And here is one interesting example. So there is a nice story behind this number. So let me first write the statement. Root 2 is not a rational. And what do I mean by root 2? So suppose if x is root 2, it means x square is 2. So number whose square is 2 is called as root 2, right? Yeah, so the story is, in fact, story is interesting. I hope all of you have heard name of Pythagoras. Pythagoras had his own school and there were two levels, level 1 and level 2. So everyone who was interested was admitted to level 1, but those who could pass level 1 and those who were good at maths were admitted to level 2. So those students who were in level 2 had some strict rules, like whatever we do in our school, you don't have to reveal it outside, and there are many rules, so many restrictions. So one of the student from level 2, he passes, was good actually, so that's why he was in level 2. Once came to Pythagoras and said, sir, in our triangle, what he mean by our triangle? So right angle triangle. So in our triangle, if we take this side as 1, this side as 1, this is not a side. Hypotenuse is not a side. Now what he mean by that? In fact, up till Pythagoras period, they were knowing only rationals. Only rationals. So for them, number was something like integer by integer, right? Okay, so he said, if we take in our triangle this side as 1, this side as 1, then hypotenuse is not a side. And by that he meant that there is no rational which equals this length. Okay, so let's see what was the problem. Kian? Kian?
Sir, I know how to prove that square root of 2 is not a rational number.
Oh, haha. Okay.
Can I say?
Wait. I'll go to next page and you help me. Okay?
Okay, sir.
Yeah. Okay, so let's say suppose this side is x. These two are 1, and everyone must be knowing Pythagoras theorem. So what we get? X square equal to 1 square plus 1 square, right? So that is 2. And what Hippasus meant was there was no rational whose square is 2. Okay, that was the statement. So there is no rational whose square is 2. Yeah, so proof is simple and there are various proofs. We'll do one proof here right now. So it's proof by contradiction. Suppose possible that x is some rational. Suppose possible x is rational. Whose square is 2, right? X is of the form some a by b. And whenever we take a rational, we always cancel out common factors and we always take it to lowest reduced form. So shall I say where GCD of a and b is 1. There is no common factor between a and b except 1. So we have taken a and b to the lowest reduced form. Whatever common factor we have cancelled, fine. Yes, so we have x square equal to 2 means a by b square is 2. Clear?
Sir, I was having a similar proof like that.
So you like to continue with this?
Yeah.
Okay. Yeah, go
Yeah,
ahead.
so I can say that a square upon b square is equal to 2, right? We can
Yes.
discuss with the square. So then we can multiply both sides by b square. A square is equal to 2b square.
Okay.
So that means a square is even.
So shall I go to next page? A square by
Yeah.
b square is 2, and here cross multiplying, right? So this implies a square is 2b square. Yeah. Just wait. Let me explain the importance of this step. It's very simple and very routine for us, cross multiply. But see, till this step, we are in set of rationals, right? Once I cross multiply, I'll end up in very small set of naturals, right? So now there are no fractions, no denominators. So this you can look at in set of naturals or integers, right? So once again, look at the idea. Set of naturals is a small set that is containing set of integers, and set of integers is containing set of rationals. Okay, so Q is much larger set, and from the bigger set we have come to the smaller set, so that the calculations will be easier. That's the idea. Okay, so a square is 2b square. Clear?
Yes, so that means a square is even. So if it is
Wait,
divisible by
wait. Yes, so step by step. Yeah, so this implies a square is even. Everyone agrees? A square is even. Yeah,
yeah, but then that means a is also even.
good. Yeah, so this implies a is even. In fact, there are two types of numbers, even or odd. Like those which are divisible by 2 are even, those which are not divisible by 2 are odd. And even into even is even, odd into odd is odd. So odd square is odd, right? So if my square is even, original number cannot be odd. Okay, so original number has to be even. So if a square is even, a is even, right? Yeah.
Yeah, so let a be equal to 2k for some natural number k. Okay, so then we can substitute a is equal to 2k in this equation. A square is equal to 2b square.
Shall I say k belongs to z? I mean, it could be integer.
Yeah, it will
Yeah.
be positive. Will be positive only.
Okay. So I put this value of a in this equation. So I get 2k square is equal to 2b square. So which implies 4k square is equal to 2b square.
Yeah, then divide both sides by 2.
Yeah. So I'll cancel out 2 from both sides, and I'll flip. So b square is 2k square, right?
Then that means b square is even, and hence b is also even.
Yes. So same argument. So b same as this. Like whatever we said for a square, same I can now say for b square. So this implies b square is even. Why? Because it is 2 times something. B square is even. B square is even implies the number b is even.
Yeah, but that is a contradiction, sir, because a is even and b is also even, but we have assumed that the GCD of a and b is 1. So they
Right.
both can't be even.
Right. So like we have written a as 2k. On same lines, we can write here b as 2 times something, right? So 2 times some L. Okay.
So, sir, basically, yeah, now we have the GCD is greater than 1, thus contradiction.
So this implies GCD of AB is at least 2. 2 is common factor, right? So which is not 1. And whereas we assume that suppose original GCD is 1. Check here.
Yeah, so that is a contradiction, sir.
Yeah. So we assume that GCD is 1. Okay. And
So hence, square root of 2 cannot be equal to a upon b, where a and b are natural numbers and the GCD is 1. So square root of 2 must be irrational.
yeah, so we assume that suppose possible, root 2 is a rational. That was assumption. And assuming that root 2 is rational, it can be expressed as some a by b, right? We got some contradiction. We got something wrong, right? And why do we get wrong? Because our assumption is wrong. Fine? Our initial assumption is wrong. Okay? So which means root 2 cannot be, or number whose square is 2, which we now call as root 2, cannot be a rational. Is that clear? Now, in fact, this was later on revealed by Hippasus to the general public, and for that he was punished. That punishment was heavy, in fact. So once all these Pythagoreans were traveling through a river, and he was drowned in that river. So for the post irrational,
Oh my.
I don't know actually. There is a story like this. So,
But sir, could we do it like a similar proof for like any number which doesn't make a perfect root?
yeah.
So
Well,
we could do it for 6, we should do it for 8 and all of that stuff.
yes. In fact, this is very interesting proof, and many what do you say, budding mathematicians learned this proof in their early days, and because of this proof, they are motivated to do something in mathematics. So one such great example is Paul Erdos, or pronunciation is different, Paul Erdős. He was a great mathematician, and when he was some 12 years old, his father was also a maths professor, maths teacher, and his father told him this proof, and he was very much impressed by this proof. So later on, he became a great mathematician. So many such mathematicians were impressed by this proof in their early days.
So, I think I thought of something. I'm not sure if this is correct. Like it's a proof for why specifically this is irrational. Um, yeah. Wait. Sudarshan. So basically like if a rational number has to be represented, it will be p upon q where both p and q are integers. So
Yes.
if p square by q square will equal to no natural like the if one integer square is divided by another integer square, it can't equal 2 unless it's like p equals q root 2, and because like only an integer multiplied by another integer can only give you another integer, and because root 2 is not an integer, therefore this is not possible.
But you have to say that step p equal to q root 2 little more precisely. So, in fact, in number theory, we'll do one more proof where we use fundamental theorem and we argue it. Whatever you are saying will make it better in after fundamental theorem in number theory. Okay? Yeah. Yes, Shreya?
Sir, we can prove it a more general thing where the nth root of k is, and if it is rational, then it has to be an integer. But I can do it by rational roots theorem.
Yes. Yeah.
Or there is another proof also.
Also, yes, Kaustubh, your raise hand.
Yes, sir.
Your raise hand. I thought you wanted to say something. Yeah. Okay. Yeah, so on same lines now, let's try to prove root 3 is not a rational. Priya, will you like to say the proof?
Yes, sir. So we let root assume for the sake of contradiction that root 3 is rational.
Yeah. So now I won't write much. So suppose possible root 3 is some a by b, right? Where GCD of a and b is 1. So they are to the lowest reduced form.
Yes, sir. So a square by b square is equal to 3.
Yeah.
So a square is equal to 3b square.
Yes.
And 3 is prime, so we can say that 3 divides a square.
Good. So 3 divides a square. 3 times something is a square, right? So this implies 3 divides a square.
Yes, sir. And 3 is prime, so it has to divide a.
Yes. Now carefully look at earlier argument. So essentially a square is even. Another way to state the same thing is like 2 divides a square. And if 2 divides a square, it means 2 divides a, right? So on same lines here, I can say if 3 divides a square, 3 divides a. Why? Because 3 is prime. Since 3 is prime, right? So this is property of prime number. Say for example, observe that 4 divides 6 square, but 4 does not divide 6, right? So that's not true for composite numbers. It's typically property of prime number. Asriya?
Yes, sir. So
So
we
3
can
divides a.
substitute a is equal to 3k.
So let a equal to 3k.
So we'll get 9k square is equal to 3b square.
9k square is 3b square. So b square is 3k square. Same argument now. So this implies 3 divides b square, which implies 3 divides b. So I get a contradiction, 3 divides a as well as 3 divides b. Whereas we started with some a and b, which have no common factor. And here we see at least there are 3 as common factor. So that's a contradiction. Right? So why do we get some contradiction? We started with something wrong. What did we start with? Suppose possible root 3 is rational. So that is wrong. Yes, Kia?
See, a number, if a number divides a square, then it doesn't necessarily have to be prime. So like 3 divides a square, then 3 divides a. It doesn't have to necessarily be prime. For example, 6 divides a square, but that means 6 can divide a also. Like if 6 divides
Yeah, because yes, that happens because 6 is in fact square free. So this happens for square free numbers. So 6 is
but I
product
can,
two
sir,
distinct
I
values.
can generalize this
Yes.
for all non-perfect square numbers. Then
Yes.
you can just do the same thing.
Yes, right. Okay, so we have done it for root 2, we have done it for root 3, and more generally, so I want to say it for general n. So what should I say? Homework. So root n is not a rational if n is not a perfect square. Okay. So now you have idea like how to prove this, right? Shall we go ahead?
Yes, sir.
Yeah. So now if I take a line, straight line in Euclidean sense, I'll mark some point as origin or 0. I'll mark some distance as unit distance. And with just ruler and compass, what I mean by that, so with compass I can draw arcs or circles, and ruler is unmarked straight edge. Unmarked, so I can't measure the distance. I can only draw straight lines. Fine? With ruler. So with ruler and compass, I can mark 2, 3, 4, and so on. I can mark all naturals. I can go backside and I can mark all negative integers like -1, -2, -3, -4, and so on. Then with some geometric constructions, I can divide line segment into 2 equal parts, 3 equal parts, 4 equal parts, 5 equal parts, and so on. So more generally, I can map 1/2, 1/3, 1/4, or any m/2, m/3, m/4, and so on. So more generally, I can map all rationals m/n. Right? Now, question was, so Greeks had a question that after mapping all rationals, is the line exhausted? So like once I map all naturals, you see still there are so many points left on the line. Once I map all integers, still you see there are so many points left on the line which are not mapped with any number. Now question is, if we map rationals, all rationals, are all points on the line so have we covered each and every point on the line? And answer is no. Why? Because so I have this line which is unit distance, and I can draw perpendicular to given line, right? I can draw with ruler and compass. So I'll draw perpendicular here. I'll mark same distance here on this line. So this is 1. And then I join these 2 points by straight line. So just now we saw that this distance is like √2, which is not a rational. And if I take this distance in 2 ends of compass, and if I mark it from 0 somewhere here, so that point corresponds to number which is not a rational. So if I map all rationals on the line, at least at this point there will be gap. This point won't correspond to any number, right? So answer is no. In fact, there are many points left on the line after mapping all rationals. So there are gaps. So a larger set which fills all these gaps, all these remaining points, that is called a set of real numbers. And in fact, there are many other definitions of reals, but at least for your level, this is the easiest definition. That a straight line in Euclidean sense, if I take straight line, if I take some point as 0 or origin, starting point, if I take any distance of my choice as unit distance 1, then with ruler and compass, I can go on mapping all naturals. Still, there are many points left on the line. I can go back and I can map all negative integers. So I can map all integers with ruler and compass construction. And still, there are many points left on the line. I can map all rationals. And after mapping all rationals, question is, are all points on the line exhausted or taken? Are they covered? And answer is big no. In fact, there are many gaps left on the line, and some larger set which covers all these gaps, that is called a set of real numbers. Okay, so for us, that's the definition of reals. Super good. Yes, Bhairav?
Sir, aren't there some real numbers that cannot be constructed by ruler and compass?
Yeah, yes.
So that like real
Like
number.
pi.
So for example, something like root pi.
Plus 2 upon 4, like a golden number.
Yeah.
And also, like, real numbers are of two types: one that can be constructed, and other that cannot be constructed.
Right.
Constructible and non
Actually,
Not cube root of 2 is not constructible.
Right. Very good.
actually, the golden ratio is constructible.
Yes.
basically, yeah, what Byros were, except constructible are algebraic and non-constructible are transcendental.
Yeah. So in fact, here algebra and geometry meet together. So most of these proofs from geometry are done algebraically. Okay.
No, actually, the cube root of 2 is an algebraic number, but it is not a constructible number.
Oh
Right.
yeah,
Right.
there's the intersection. Yeah, those which are not constructible are not. Yeah, they are transcendental.
So see that transcendental are surely not constructible, but what you're saying was
The other way is incorrect.
yes, we were.
Are there more real numbers or are there more natural numbers?
Real.
Yeah. So in fact, in this infinite sets, there is again hierarchy. So there is something in infinite called as countable and uncountable. So countable is like
That's not.
smaller infinity, and uncountable is like larger infinity. So this was all done by Cantor. So reals are uncountable, and whereas naturals, integers, rationals, they are all countable. So in some sense, though any subset of integers and integers is subset of rationals, in say theoretic sense, they are equivalent. So in some sense, they have equal number of elements. Yeah. So reals is a big set, uncountable, as compared to naturals, integers, rationals. Hi, Shreya.
Sir, rationals are not countable because it.
No, rationals are countable. So I can, there are some tricky arguments. So like, for example, I can write in some infinite matrix form something like this. 1 by 1, 1 by 2, 1 by 3, 1 by 4, and so on. Then 2 by 1, 2 by 2, 2 by 3, 2 by 4, and so on. 3 by 1, 3 by 2, 3 by 3, 3 by 4, and so on. So I go on counting this way. First number, I'll go this way.
Yes, sir, but this is not in order. If I give you a rational number, you cannot tell me the next rational number.
In that sense, you can't say next number, but see, that is up to your arrangement on line. But if I arrange this way, I can always tell you the next number.
Next largest rational number.
Not exactly largest, but I can give a function which which in some sense numbers the rationals like first, second, third, and so on.
Yes.
So not with order, but I can always number them in a suitable manner.
Sir, I had a question.
Yes.
So I didn't quite understand what you mean by uncountable.
Oh yeah. So countable is something which I can assign numbers like first number, second number, third number, and so on. Or to be more precise, and I can give a function from set of naturals to whatever that set, okay, which is bijection 1, 1 on 2. If I can give such a function, such a map, that is countable. If I can't give such a map, then that is uncountable. Okay, but right now we won't go into that function theory. It will be too much at least at this level. But maybe someday we'll be learning functions. So I'll talk more about this later. Okay. Yeah, shall we go ahead? So I hope now all of you have some idea of the numbers with which we work in our day-to-day maths, like set of naturals, that is contained in set of integers, that is contained in set of rationals, that is contained in set of reals. So right now we have reached up to reals, but in fact further there is extension. The reals are contained in complex numbers and so on. And those real numbers are divided into two parts. One is set of rationals, and those reals which are not rationals are called as irrationals. Irrationals. So now I can say root 2 is irrational. Note carefully, we haven't said so far root 2 is irrational. We said root 2 is not a rational. Yeah, so root 2 is not a rational. Root 3 is not a rational. Or more generally, root n is not a rational if n is not a square. And now we have some name for all these numbers. So root 2 is irrational, root 3 is irrational, root 5 is irrational, and so on. So two more standard examples of irrational numbers are pi and e. They are also not rationals. Okay, so shall we go ahead? Ritwik?
Sir, why is 2 irrational?
No, 2 is not irrational. Root 2, root of
So,
2.
I mean, why is square root of 2 irrational?
That we proved because it is not a rational. We proved it. Root 2 is not a rational, right? Is that okay? Ritwik?
Yes, sir.
Yeah. So we proved that root 2 is not a rational, root 3 is not a rational, and so on. So those numbers which are not rational, now we can have a name for them. They are irrationals. Yeah, so far good. Now, as far as rationals are concerned, we know rational plus rational is rational. The set of rationals is closed under addition. Addition of two rationals is again a rational. the way we define, like A by B plus C by D is AD plus BC by BD, which is again a rational. Okay. Or rational into rational is again a rational. So like A by B into C by D is AC by BD, which is again rational. Okay. The question is on same lines. What happens with irrational numbers? If I add two irrationals, irrational plus irrational, is it always irrational? Always.
Not
No,
necessarily.
sir.
Sadly. Let's
So
take
that,
You have root 2 plus 2 minus root 2.
okay, yeah. So root 2 is irrational, and on same lines, one can prove that minus root 2 is also irrational, right?
Yeah.
So if I add these two, then the answer is 0, which is not irrational, which is rational. 0 is rational. Okay. So here is at least one example where addition of two irrationals is not irrational. What happens with multiplication? Irrational into irrational will be always irrational.
No, sir. Root 2 into root 2 is 2, not irrational.
Yeah. So root 2 into root 2. So both are irrationals, but the product is 2, which is rational. What happens with power? Because power is not some standard binary operation. So if I take a rational raised to rational, will it be rational?
No.
Yes.
Yes, sir.
Sir, I'm not
No,
sure.
sir, not always. 2 raised to 1 by 2 is root 2.
Oh, yeah. So 2 is rational. Everyone agrees. Half is rational. But 2 raised to half, which we denote by root 2. And just today itself we proved root 2 is not a rational. So here is one nice simple example that rational raised to rational may not be rational. Ritwik?
Sir, but think about this. I mean, rather those rational can mainly be irrational, sir. Mostly mainly. So it's due. Like suppose 3 to the power 2 by 3. So sir, it's irrational because we cannot denote how to calculate it.
Yes, yeah. Okay, so now little tricky question. Irrational raised to irrational. Will it be irrational? Always? Shreya?
No, sir, not always. We can take 2 raised to log 3 base 2.
Yeah, but 2 will be in that case irrational, right? So you are giving example of rational raised to irrational is rational, right? I want both numbers to be rational. Ritwik?
Sir, it's not possible, I think.
So what do you mean irrational raised to irrational?
So I think it cannot be denoted. I mean, like, for example, so
like 3 is there, sir. And if we say like 3 to the power 3 to the power 3 by 4. So we cannot denote like really what will be the answer.
But 3 and 3 by 4 both are rationals. I want something irrational raised to irrational.
Oh, sir, then like 2 by 3 raised to 3 by 4.
2 by 3 raised to 3 by 4. But both of them are rationals. I want both these numbers to be irrationals. Rhea, Asrividya.
Sir, can we consider root 2 to the power root 2 irrational?
Yeah, that's a good example. Okay, so look at root 2 raised to root 2. Okay, in fact, there is a tricky argument with this. Let me go to next page and give the argument. Can I go to next page?
Yes, sir.
Yeah. So the argument is in fact tricky. So you look at root 2, which is irrational. Root 2 is irrational. And consider root 2 raised to root 2. If this is rational, then we have got counter example, right? If this is rational, we are done. But it's difficult to check. So in fact, now it's proved it's not a rational. So if it is irrational, otherwise root 2 raised to root 2 is irrational. And in that case, you again look at root 2 raised to root 2 whole raised to root. Okay. It's around 1 bracket. Yeah. So root 2 raised to root 2. This is my number. Suppose if this is rational, we have got a counter example. Irrational raised to irrational is a rational. But suppose if it is irrational, then you look at this number raised to root 2. Again, I have case like irrational raised to irrational, right? And let's check what's this answer. So what is this? If I simplify powers, this is same as root 2 raised to 2. All of you agree? By laws of induction,
Yes, sir.
powers get multiplied. Root 2 raised to 2. And what is root 2 raised to 2? That is 2, which is a rational. So we can have example where irrational raised to irrational can be rational. Yeah, Anish, this example will work. Will you write it for everyone in the chat box? Yeah, shall we go ahead? So, irrational raised to irrational can be rational. Rational raised to rational can be irrational. And we have seen such examples. Fine?
Sir,
Yes?
Sir,
how come if root 2 raised to root 2 is answer, then we are done?
So I want to just a minute. Let me go to
Why?
earlier.
How come we are done if
Yeah,
root 2
just,
raised to root 2 is
yeah.
rational?
So listen to the actual question. So is irrational raised to irrational always irrational? Answer is in fact
Okay.
no.
So
No.
you're saying if root 2 raised to root 2 is rational, then we're already done because root 2 and root 2 are irrationals and the product is rational. So we're done. But
Right.
irrational, you're saying then root 2 raised to root 2 raised to whole raised to root 2, you're saying then that will be root 2 square. So that is 2. That's rational. Okay,
Right.
sir.
Right. Good.
Sir,
Yes.
sir,
it means like the irrational power irrational may or may not be irrational, right?
Right, right. Good. Yeah, shall we go ahead?
Sir, I have a question.
Yes.
So what if we take this square root to 5 upon pi? So what, I mean, it cannot be anything, can it?
What raised to pi?
Square root of 5 goes, I mean like square root 5 raised to pi. Sir, not 5, pi, pi.
Oh. In fact, such questions are really difficult questions. And one number theorist, Alan Baker, who has written a nice book on irrational numbers. And he has given various techniques to show different numbers are rationals, irrationals, and so on. Yeah, so maybe those who are interested in doing this rational, irrational business, so there is a nice book by Alan Baker, Irrational Numbers. Anju has raised hand.
Sir, is root 2 raised to root 2 itself?
Root 2?
Is root 2 raised to root 2 itself?
In fact, now it's proved, so it's a difficult question, but it's settled now that root 2 raised to root 2 is not a rational. This is irrational.
So, if we open it like 2 raised to half.
Without knowledge of this, we argue this way. You look at root 2 raised to root 2, there are two chances. Either this is rational. In that case, we are done. We have got example where irrational raised to irrational is rational. Or otherwise,
Sir, I understood the logic. I'm just asking, is root 2 raised to root 2 itself?
Root 2 raised to root 2 is?
Is it root 2 itself?
No. That will be different. See, root 2 raised to 1 is root 2, right? And root 2 raised to root 2 is approximately some 1.4 something. So it will be bigger than root 2 raised to 1. So this
But
is
then can't we write it as 2 raised to half raised to 2 raised to half?
Yeah.
In that case, wouldn't it?
That is bigger than root 2 actually. 2 raised to root 2.
So we can't write root 2 raised to root 2 as 2 raised to half raised to 2 raised to half.
That you can write. This is 2 raised to half raised to 2 raised to half. That you can write. And even you can use laws of indices here. That is like 2 raised to half into 2 raised to half. But
So we can't multiply half into half into 2.
Now you can't simplify much with this. So this is like 2 raised to 2 raised to half upon 2 raised to 1. So it's 2 raised to minus half.
Oh, okay. Okay, sir. Thank you.
Yeah. Bhairav?
Sir, what is your formal definition of raising numbers to irrational powers?
Yeah, that's a good question. Very good question. Yeah. So suppose if I have some positive number let's stick to positive numbers because if we have negative numbers and if we take some fractions, we may get complex numbers. Yes, so suppose a is greater than 0. So I can define a raised to some natural number as follows. So a raised to n is like a into a n times. And even this can be done precisely using induction. If n is natural number, a raised to n is 1 if n is 0. This is my definition. And a raised to negative integer. So it's like 1 by a raised to minus n if n is negative integer. Okay, so for example, a raised to minus pi is like 1 by a raised to minus pi, that is a raised to pi. And now a raised to pi is defined, it's like a multiplied 5 times. Right? I can define it for integers. Okay. Now with that further I can define it for rationals. So let's see. Like suppose if I want to define some number raised to 2 by 3. Okay. So what I'll do is
You're never going to become a doctor. I know it. Oh, you. But I have chosen your destiny. Papa is being the doctor. If you will become if you will become an astronaut or a doctor. So I got my vote.
Somebody's audio is on. Yeah, so now suppose I want to define some number raised to half. Okay. And this is equal to suppose y. So essentially y square is equal to x, right? So given number x, I'll try to find some y whose square is x. And one can prove theoretically that such solution exists. Okay. So y square equal to x has a solution y in reals, and that y is called as x raised to half. Or more generally, if I take y raised to n equal to x, that has a solution for every positive x, and then that y is called as nth root of x or x raised to 1 by n. So I can have 1 by nth root. Okay, and once I have 1 by nth root, I can take mth power. So like for example, if I want to define x raised to 2 by 3, so firstly x raised to 1 by 3 is defined, and then I'll take square of that. So that will give me x raised to 2 by 3. Okay, so with that we can define rational powers. And now suppose I have some irrational number like root 2. So you find some sequence of rationals which converges to root 2, x1, x2, x3, and so on, which goes to root 2, sequence of rationals. Converge means which goes very close to root 2. So converging to root 2. Then you look at some number a raised to x1, a raised to x2, a raised to x3, and so on, a raised to xn. So this sequence converges to whatever number, that number we call as a raised to root 2. Right? That's our definition. So more generally, instead of root 2, you can replace it by any irrational. So x is any irrational. You take a sequence of rationals xn converging to x, which is shown this way. This is the notation. Xn converges to x. Then I look at sequence a raised to xn, and what are the limit of this? That we define as a raised to x. So that's the definition of a raised to irrational. Okay. Who asked the question?
So do we all yes. Do we always know there will be a secret sequence of rationals converging to any irrational number?
Yes. One can always produce some sequence of rationals converging to irrational, or vice versa. Sequence of irrationals converging to rationals.
Yeah.
Yeah. Will we go ahead? Ashreya?
So actually, two doubts. First, your definition of x raised to 1 by 2 is different from root x. It's not taking the absolute value.
Which absolute value?
The negative root is also counted.
No, I do not right now the negative value. So
Okay, so x raised to 1 by 2 is also x raised to 1 by 2 is only the positive value.
yeah, so in fact, yeah. So generally there is a convention that if you put negative sign before square root symbol, and that is negative square root. And if I don't put any symbol, that is taken as non-negative square root.
Yes, sir. But in the previous definition for the power of a rational number, that is not there.
Where?
Previous page.
This
Yes, sir.
one?
Yes. So there are two different values for y.
Yeah, so yes. So in fact, there will be two values of x. Not two values of x, two values of y, for which y square will be x. Right? Because in fact, whatever you get, whatever square you get for a number, same square you get for minus of that. So square roots are always that. In that sense, there are two square roots.
Okay. Also, sir, how would you, if you take a negative value for x,
No,
then
right now I said we are talking about only positive numbers. Otherwise, if you take negative numbers, you may land up in complex numbers. You may not.
yes,
real
sir.
answer.
But if we multiply both sides by 2, then we are done.
Where?
In the fraction, if instead of 1 by n we say 2 by 2n, then we'll get the positive value.
Yes.
So another doubt: how do you find the limit of such for irrational power?
Which one?
In this, for finding an irrational power, how do you find the limit?
So in fact, there are some techniques from analysis. So right now we won't go into those details. Okay, but I can give you example of sequence. So like for example, root 2 or every irrational has infinitely many decimals. So it's like 1.4, 1.42 and so on. So I can take x1 as 1, x2 as 1.4, x3 as 1.41, 0.414. So gradually I can go on increasing one decimal at every time. Okay, and this is one example. It's not the only sequence which converges to root 2. There will be infinitely many sequences converging to root 2. So you can choose any such sequence and you can go via that sequence.
Okay, so just have to take many terms of that sequence and see where it's converging, or is there a better method? Okay, thank you.
So, but how exactly do we calculate it after finding like xn, x of n?
What?
We can only find a to the power of root 2 if we get like some rational number close to it, which is like x or like
Yes.
n. So I mean, we can never know what that value is. So how exactly do we still find the answer?
In fact, there are some techniques from what is called as analysis, which is little next to algebra and geometry. So maybe at least at this level, I won't be interested in explaining those things. They are little different, and for Olympiads, we don't need those things. But I said just because the definition should be clear. Maybe if you are interested, you can read some good books on analysis. So there is this book by Mathematical Analysis by Rudin. Okay, by Rudin, Walter Rudin. Yes, shall we go ahead? Anju has raised the hand. Anju?
Sir, by law of indices, isn't a raised to m raised to n raised to r a raised to m into n into r?
Yes, yes.
So, in that case, if we do root 2 raised to root 2, won't we get root 2 itself? Because we get half into half is 1 by 4. 1 by 4 into 2 is half. And then 2 raised to half is root 2.
No. What you were saying was not clear to me, like how you said those powers.
Sir, a raised to m raised to n raised to r is equal to a raised to m into n into r, right?
M, A raised to M.
Raised to n
Uh,
whole raised to r. This is equal to a raised to m into n into r.
right, correct.
So 2 raised to half raised to 2 raised to half.
But now this is not two. This is not something like this. This is that number n is itself 2 raised to half. Right? So we don't have three
Oh.
numbers here. We have two numbers, m and n.
Okay, okay, sir. Sorry, I didn't realize we can't split to n. Yeah, okay. Thank you, sir.
Okay. Find the sum. Find the sum. Let us simplify the expressions. 1 by 2 root 1 plus 1 root 2 plus 1 by 3 root 2 plus 2 root 3 plus so on up to 1 by 100 root 99 plus 99 root 100. There is a well-known name in Olympia training, T2 and rescue, and he had a math competition named Purple Comet. So this question is from Purple Comet. Yeah. So another way to write this sum compactly is following. So in general, what is the term? It's something like this. If I call this number as say n, shall I say it's like n plus 1 times root n plus n times root n plus 1. Okay. And this sign stands for addition or summation. It's Greek letter sigma. So sigma notation stands for addition. And I'll say n goes from 1 to 99. So this first term is for n equal to 1 and last is corresponding to n equal to 99. Is that okay? The notation clear? That's called as sigma notation, summation notation. So I can write it as sigma n goes from 1 to 99 and general term is 1 by, so the form 1 by n plus 1 root n plus n root n plus 1. Good. So I'll try to simplify this general term and how we can simplify. So process is called as rationalization. So let's see. So I'll multiply and divide by same term. So it's as good as nothing. And what term I'll multiply? N plus 1 root n minus n times root n plus 1. So suppose my term is something of the form 1 by a plus b, I'll multiply and divide by a minus b. If my term is a minus b, I'll multiply and divide by 1 by a plus b. Yeah, so what's the advantage? That now in denominator I get something like a plus b into a minus b. So it simplifies as a square minus b square, right? So I'll write this as n plus 1 into root n in numerator minus n times root n plus 1 upon n plus 1 root n square minus n root n plus 1 square. Okay, agree? So it's like a plus b into a minus b. And product is a square minus b square. So it's like n plus 1 root n n plus 1 root n whole square minus n root n plus 1 whole square, right? Now you simplify that denominator and I'll go to next page then. And yes, Anish, that's correct. Okay, so n plus 1 root n minus n root n plus 1 upon n plus 1 square into n minus n square into n plus 1. Check whether I'm correct. Have I written correctly?
Yes, sir.
Now I can take something common in denominator. So it's n plus
Into
1.
n plus 1 into 1.
Consider what is that? N plus 1.
So basically, I have n into n plus 1 into 1.
And I'll get n plus 1 minus n, right? Which is
Which
1.
is 1.
So it's n plus 1 root n minus n root n plus 1 upon n plus 1 into n. Let's separate out the two terms. So it's like n plus 1 root n upon n plus 1 into n minus n root n plus 1 upon n plus 1 into n. Let's check. It's something like a minus b by c, and write as a by c minus b by c, right? Now we have some cancellations. N plus 1 cancels here. Even 1 root n will cancel, and I'll get 1 by root n minus here n cancels. 1 root n plus 1 will get cancelled, so I'll get this one. In fact, there are many ways you can simplify and reduce it to this form. So it's fine if you have done by some other technique, other way.
So could you show the previous slide for once?
So my general nth term is 1 by root n minus 1 by root n plus 1, right? So let me write here itself. So my first term is 1 by root 1 minus 1 by root 2 plus second term is 1 by root 2 minus 1 by root 3. Third term is 1 by root 3 minus 1 by root 4 and so on till the last, which is 1 by root 99 minus 1 by root 100, right? And now you see, so this is called a stereoscopic sum. Alternately, you get plus minus signs. So minus root 2 plus 1 by root 2, minus 1 by root 3 plus 1 by root 3, minus 1 by root 4 plus 1 by root 4, and so on up till this one. Everything will cancel. So essentially what I get is first term minus the last term. So first term is 1 by root 1, that is 1, minus last term, that is 1 by root 100, so 1 by 10. So my answer is 9 by 10. Yeah, good.
Sir,
Yes.
can you go to next page?
Yes. Yeah, shall we go ahead?
Yes, sir.
So one more question. Given a root a plus b root b is 183 and a root b plus b root a is 182. Find 9 by 5 times a plus b. In fact, this is some PRMO question, and in PRMO or even IOQM, answers are expected to be some 2-digit integer. So just to have integer solution, instead of asking some a plus b or find a, find b, they ask 9 by 5 times a plus b. So that is just to get some 2-digit integer answer. So this was PRMO 17. Yeah. So we need some algebraic identities. Maybe just to make it simpler, let's call root a as x and root b as y. Okay, so let x equal to root a, which means x square is a and y square is b, right? So this first equation I can rewrite as x square into x, so that is x cube, plus y square into y, that is y cube, is equal to 183. And second equation we can rewrite as x square y plus xy square is equal to 182, right?
So this is x plus y the whole cube equals x square x cube plus.
Yes, sir. Good, good. Yeah. Just a minute, I'll go to next page and you tell me the identity. Okay, all of you agree with this? Shall I go to next page?
Yes.
Yeah. So x plus y, who was that? Who said that? So we know x plus y cube is x cube plus y cube plus 3 times xy into x plus y, right? Or, I mean, that is 3x square y plus xy square. All of you agree with that? That's a standard algebraic identity for cube. And we are given what is x cube plus y cube. So that is 183. This part is 183 plus 3 times this part is 182. Can you simplify?
One 183 plus 546. So 720.
729, sir.
729.
Yeah, 729.
X plus y equal to 9.
Okay, so all of you agree x plus y is 9. 9 cube is 729. Okay. So x plus y is 9. And what we want answer to be 9 by 5 times some a plus b, right? So we want, so let's write in xy terms. So this is 9 by 5 times x square plus y square. So I want x square plus y square. Okay. So we have got x plus y. And I want x square plus y square. So x square plus y square into x plus y is x cube plus y cube plus x square y plus xy square. Is that right? Multiply every term into every term. This into this, this into this, this into this, this into this, right? So I get 4 terms, x cube, y cube, x square y, xy square. And out of which I know x plus y, so this is 9. And this is 183 plus this is 182. So that is 365. So 9 times x square plus y square is nothing but a plus b. So 9 times a plus b is 365. And what we want is 9 by 5 times a plus b. So 9 by 5 times a plus b is, I have to divide by 5. 365 by 5, that is 73. Right? Yeah, so today we discuss rationals initially, then we got later on took the idea of what is irrational or what are Indian real numbers, right? Then we saw some nice examples where rational raised to rational may not be rational, or irrational raised to irrational may not be irrational. And during that, some nice questions were discussed, like how do we define irrational power of a number? Okay. But something like convergence of sequence, etc., that falls into category of analysis or advanced calculus. And for Olympiads, calculus is not suggested or not allowed. So those who are interested, you can read some good books, standard books. Like I have given some references. One nice reference is Mathematical Analysis by Rudin. So those analytic things we may not be able to discuss here. Yeah, so shall we stop for today then?